Now, at last, we implement the final algorithm. So I put here side by side the implementation we had in CoCoA 5, so we can compare with implementation in CoCoALib. So we had the function taking an input as an input to the ideal. So here I have more explicitly in C++ that my GBasis takes an ideal and returns a vector of ring LM. Then our first step was to settle that we were going to use the verbosity, and this is how the way it is done in CoCoALib. So we have actually to write a channel for writing the verbose output of our function. So these not only writes the name but creates a channel for printing. Then we had the initialization. So we start with the GB and pairs the empty list. And then here we are. So the Grosvenor basis is going to be a vector of ring LM. For the list, for the pairs, instead I prefer to use a list. So what's the difference between a list and a vector? A vector is like an array, or is like in CoCoA, it is in CoCoA 5, we have a list of places with indices. It is a big block of memory. A list instead is a linked list, which means that we have an object linking to the following object, linking to the following object. So we have many blocks sparse in memory. So why should we prefer that? Because that allows to sort things more easily, or to delete things from the middle of the list, or to delete easily the first element in the list, because you just eliminate one block instead of having to remove one block and shift everyone by one position. It is very nice that many operations in C++ for list and vectors are essentially have the same name and can all be used in the one or the other interchangeably. Of course, the difference is in efficiency. It depends on what you want to do with this list or vector of elements. If you want to remove the first element one at a time, then a list is better, because you just remove one element and you do not change anything in the rest of the list. That is again something that you can do with CoCoALib. You cannot do it in CoCoA 5 because we chose one structure, which was the generally the easier to maintain and use it. Okay, so then we start the minor cleaning. So here we have a for each f in the generators of I, and this is the similar constructor in C++, in C++ 14 and upwards. So this is auto is a nice way of saying I don't care what the type is, you detect it yourself. It is very nice because it is almost like having CoCoALib usable as CoCoA 5. So auto means the compiler detects by itself what that object is. So for each f in the generators of I, do compute the normal remainder and assign it to G. If the result is not 0, then push back. This is the way of adding an element at the end of one vector. So the name of the vector, GB, push back, and as an argument, the object we want to put at the tail of the vector. Then we have to do the pairs. This is a very nice constructor, but has a lot of work behind it, and we just unroll this work. And so we say the index of G is the length of the Grosvenor basis of GB as it is now, -1, because remember that they start from 0. So this is the index of my new element, and so I have to add all the pairs with the index n and the index of G, with n that goes from 0 to 1 before the index of G. So this is the usual for loop, and so we take the list of pairs and we push back GB pair, the constructor we wrote just before, with the index n and index G. Okay, so we are at this stage. Now we have done the minor cleaning at the beginning. Then we want to do the verbosity step at level 8. We want to print the first informations, the informations we start from. And this is the way you do it in CoCoA. So you write verbose, which is the channel. I should have done that here. The channel, the printing channel of the verbosity. So you just write verbose 8. This is easy in CoCoALib than in CoCoA 5. Verbose 8 and what you want to print, which is the same that we had here. We want to write the Grosvenor basis to be the first generators we have and the number of pairs we have. Then we have a while loop, and while there is at least one pair, do this cycle. So we have to declare we are using a pair. So I say that we are going to use a pair P. We have we need to say two indices, which we are not going to use because we are just going to redefine it at the beginning, because when I when we defined the class GPair, we said that the only way to create a GPair was to give two indices, GB pair. So we make a random one. We're going to destroy it the next step. That's not too bad. It's outside of the while loop. Then while the list is not empty, again, we have to use the C++ definitions for the list. This is a list. To see if a list is empty, this is the command. Number of the name of the list, point, empty, open bracket, close bracket. This tells us if this list is empty. So while not this list is empty, what do? We take the first list, the first element, and then we reassign to the pairs the tail of the pairs. So this is done more efficiently in C++. So P is pairs dot front, which means the first one, and then there is this function which pop front, which just kills the head of the list. And it is very efficient. It's just pointers, and it is not like this function, which instead has to copy all the list of the tail of the pairs. And here there was a comment at the verbosity level 5, and here is how we do it in CoCoALib. So we write verbose 5, that means from 5 onwards. We write, this is the current pair. Then we compute the normal remainder, as we did here, normal remainder of the S polynomial of the pair, the GB with the index P first index, GB of P second index, which is P1 and P2 in this case. And then if the polynomial, the normal remainder is not 0, then we push back in GB the polynomial, and we take the index of this new polynomial as before. It is len of GB minus 1, and we add all the pairs as we did before. We push back all the pairs n comma index of G with n that goes from 0 to the index of G excluded. Okay, so we translated the code from CoCoA 5, and at the end, I added an extra printing. So after I this purpose here is after this, not the 0, then at this point it tells me, I think I put it in the wrong place. Yes, I did. Oops. Okay, epsilon. So if it is not 0, then I print there is a new element, and it tells me the length of the pairs at that stage. And at the end, return GB, as we did in CoCoA 5. So now okay, cleaned up. This is my C code. And then I go back to my program. Here I was, so I add this last part of the code. So this was the original ideal I had. We had already computed the Gröbner basis, so we print it out again, and we compared the result with what we computed. We set the verbosity level to 5. You can even set to 8 and see what else it prints. And we compute the Gröbner basis using my G basis now. And then we can ask, this is an interesting exercise if you want to suffer, to write my interreduce instead of using the interreduction from CoCoALib. So this is the reduced Gröbner basis. That is what CoCoA gives you. And then I recall one example that was quite expensive in CoCoA 5. Well, quite expensive. It took half a second. And we try computing the same in CoCoALib. So I show you also how to deal with the CPU time in CoCoALib. So in CoCoALib, the time is a double. Of course, we don't have a double in CoCoA 5, so we used a rational number. Here it is a double as a floating point number in C++. So this is just a number. So this moment as a number double, compute the Gröbner basis, and then I write the time as the CPU time, this time after the computation of my G basis minus T0. That was the time before the computation of Gröbner basis. That tells me how long it takes now in CoCoALib to compute the same function, the same example. I want to tell you that this computation is really not identical to the one we did in CoCoA 5, because in CoCoA 5 we used normal remainder LPP. Here we use the full reduction, but the obvious advantage is given by the fact that we're using lots of specific data in C++, like using lists, like doing the operations very efficiently without going through the interpreter. This means that if you want to write some algorithm which lots of very basic computations that you do millions of times, then you'd better do it in CoCoALib. If you have an algorithm calling like Gröbner basis in CoCoA 5, some heavy examples, heavy functions in CoCoA 5, then probably it goes pretty well, because the overhead of the interpreter is very little compared to the complexity of the computation that is running in the core in CoCoALib. So now, let's see. Let's compile. Oh, this is the shell. Okay, here it is. Ah, that's a spoiler. Ah. So I compile. That's it. And X MyGBasis. Let's see. So this is the new part. This is the Grosvenor basis computed by CoCoA at the beginning of this example. And this is the computation run through MyGBasis with the verbosity at level 5. So it prints pair 01, 02, 12. And so this is MyGBasis at the end, which is different from what was given by CoCoA, because CoCoA also does the interreduction at the end. So if we do the interreduction at the end, it is almost the same. We just has the sign different because I forgot to do the mnemonic to compute reduced Grosvenor basis. And this is the example that we saw in CoCoA 5. In CoCoA 5, the time was half a second, and here you see it is 10 times faster. So now you should do your own experiments and start changing here and there, change the printout, change the functions, compare with CoCoA 5, do whatever experiments you want, and enjoy CoCoA and CoCoALib.